Hi, my name is Shahnawaz. In this lecture, we are going to prove some results regarding the basis for a topology. But before that, let us recall what we did in the last two lectures. So, if we have a set X, then we call this fancy T to be a topology on X, or we call this pair a topological space. If this T is why this T is the collection of subsets of X, uh, where each subset of this T is called open set of X. So this is called the topology on X if it satisfies the following three conditions. The condition first was that this T consists both sets, i.e. the empty set and the X itself. So these two elements must belong to this collection. So this was the first condition. Then we have the second condition, that this T is closed under arbitrary union, i.e. if this fancy D is any subcollection of, so if this is a subcollection of tau, then if we look at the union of all elements of D, then this set has to be in this collection. So this means that this fancy T is closed under arbitrary union. Then finally we say this collection has to be closed under finite intersections, i.e. If a1, a2, so on, an are the elements of this collection, then their intersection must be an element of this fancy T. Note that this is a set here, so this set has to be in this collection. So if this T satisfies these three conditions, then we call this T to be a topology on X, or we call this pair a topological space. Now there is this definition that any element, so if A is in this collection, so if A is any element of this collection, then this A is called an open set of X. So then A is called an open set of X, and vice versa, i.e. if A is open in X, then A is an element of this script T. Then we defined the basis for a topology. So this is the definition for the basis for a topology. So suppose we have a set X and a collection, this fancy B, of subsets of X, then we call this B to be a basis for a topology on X if this B satisfies two conditions. So we are not mentioning anything about the topology for which this B is a basis, but let us first recall when we call this collection fancy B to be a basis of X. So this B has to satisfy these two conditions. The first condition is that if we have any element this little x in this big X, then there must exist an element B in this collection which contain this little x, such that this x is contained in this element B. So that means here we have this space X here, and we have an element X. So for this element there must exist an element B in this fancy B which contain this X. And the condition second is that suppose there are two basis elements B1 and B2. I mean there are two elements, say B1 and B2 in this script B, which contain X. These B1 and B2 are the elements of this fancy B. So if this is the case, i.e. if X is in the intersection of two elements in this collection, then there must exist another element b3 in this fancy b, such that this x is in b3 and this b3 is contained in this intersection, i.e., so let us erase this. So suppose we have two elements, say b1, so this is b1 here, and we have another element, say b2. Now we have this condition here that this x is in b1 as well as in b2. So suppose this is our x, so note that this x is in b1 and b2. So if this is the case, then we should be able to find another element in this fancy b, say b3, which contain this x, i.e., we should be able to find a basic an element b3 in this fancy b which contain this x, and this b3 must lie in this intersection. Then we call this fancy b to be a basis, and any element b in this fancy b is called a basis element. So these b1, b2, b3, these are all basic elements, I mean the basis elements. Then we proved that this basis generates a topology on x. So if we have this set x and this b is a basis of some topology on x, then this b generates actually a topology, say t. Let us write tb, and this x, this fancy b generates a topology on x which is this tb, or if there is no confusion, let us write this simply t. So now there is this question, if this t is a topology generated by these elements which are in this collection, then how an open set in x looks like, i.e., if u is in tau, which means this u is open in x, then how this u looks like, I mean what is the criteria for u to be an element of this collection tau. So we say that this u is in this fancy t if and only if for each x in u we should be able to find a basic element b in fancy b such that this basic element contains this little x, and this basic element must be a subset of this u. So this is the criteria for u to be in this collection. So if this u satisfies this expression here, then we call u to be an open set of x, or equivalently we say this u is in this collection. I mean we say u is in this topology. Now there is again this observation that every basic element b is in topology. The reason is that if x is in b, then this recall from this definition here, so u is said to be an element of tau if for any element x in u this expression is satisfied, i.e., if we are able to find a basic element b for which this expression is true. Now what we want to show, we want to show this b is in tau for all b in this script b. So these basic elements will be in tau if this condition is satisfied, i.e., if we choose any basic element b and an element x in x, we should be able to find a basic element. So in this case that basic element will be b itself, i.e., this x is contained in b and this b is contained in b. So that means this b is an element of this tau because this b satisfies this condition, that is given any x in u we have a basic element b in b such that X is in B and B is contained in U. We simply just replace U by B, we are done. So this is this observation that if B is a basis for a topology tau on X, then these basic elements are in tau, i.e. this collection is actually a sub collection of tau. Now let us prove our first result regarding the basis for a topology on X. But before that, one should keep in mind that if X is a set and B is a basis for X, then this X is actually the union of all basic elements. So this we have already proved in the previous lecture, so there is no need to prove this again. So we have this first lemma. So it says that let X be a set and let B be a basis for a topology say T on X. So this is our hypothesis that X is a set and B is a topology for B is basis for this topology tau on X. Then this T equals the collection of all unions of elements of B. T equals the collection of all unions of elements of B. So what this means that, so we have given here X as set and this T is a topology on X, and this topology is generated by B. Then what we have to prove? We have to prove this T is actually the union of, the union of all, this T is actually equals the all unions of elements of B. Now there is this term all unions of elements of B. So what we mean by this? So let us suppose that we have the set X and this B is the topology basis for a topology T on X, where this B fancy B have, for example, 3 elements. And note that this T here, we consider this T to be generated by B. Then we have to prove this T is actually the all unions of elements of B. Now what are the all unions of elements of B? So first of all, it must consist the element of B1 union B2 union B3. First element is the union of all these elements, which in our case is the set X, because note that X is union of all basic elements. So then we have these unions, which consists of just 2 elements, B1 union B2, B2 union B3, B3 union B1. Then we have the union of elements which just contain one element, so B1 B2 B3. Then we have the empty union which does not contain any basic element, that is the empty union. So this is our topology. So this topology has in this case 1 2 3 4 5 6 7 8 elements. So now what we have to prove, we have to prove this topology here. This is actually the uh, this actually equals the collection of all unions of elements of B. So we have to prove this T is this topology here. Not only that, so if U is any element of this topology, we have to prove this U is actually the some union of these elements. So this is vice versa condition, i.e. This topology is actually the all unions of elements of B, and if U is any element in this topology T, then this U must be equal to the union of some union of elements of B. Let us prove this. Uh, so let us prove. So first of all, we are going to prove that if I take union of any number of elements of this fancy B, that union has to be an element of tau. So let D be any sub collection of elements of B. So this D consists the elements from B. So since each basic element is in tau, so this is the previous observation that B is in the topological space tau for all B in, for all B in B. That means every element in this collection here is also in tau. So since each element in this fancy B is in T, hence every element in this fancy D is also in T, since D is a sub collection of B. That means any element in this fancy D is also in T. Now T being a topological space implies this T is closed under arbitrary unions. So now T being a topological space, T be a topology on X, T be a topology on X, we have, so this T is closed under arbitrary unions, i.e. If I take any union of elements of T, that union has to be in T. In particular, if I take the union of elements of D, then that union has to be an element of T. So we have, if I look at this union where this D, if I look at the union of these elements D, where this D is in this self D, that union element has to be an element in tau. So far we have proved that if I take any union of these basic elements, that union has to be an element of this fancy D. Now what we have to prove, that we have to prove that any open set, i.e. any element in this T is actually the union of these basic elements. So conversely, let U belongs to this fancy T. So this U is any element in this fancy T. Now what we had to prove? We had to prove this U is actually the union of these basic elements. So if U is in T, i.e. if U is open, then by note that this T is the topology generated by B, and remember that an element U is in tau if for any element X is in U, we can find a basic element B in B such that X is in B and B is contained in U. So then by definition of T, because T is a topology generated by B, so then by definition of T, for each X in U, we are able to find a basic element B in B such that X belongs to, let us call this basic element Bx. So X is in Bx and this Bx is contained in U. Now this is true for any X in X. So if we have this U to be an element of U, so then for any X in U, we can find a Bx in U such that this X is in Bx and this Bx sits in U. So this is true for any Bx. So i.e. if I look at all these basic elements, then this has to be a subset of U, because if I look at this element Y, then we can find By here, which is in U. Now since all these basic sets sits in U, so is their union. So this is the one way. Now to prove U is contained in there, we will proceed as follows. So also let X be any element in U. We had to prove this X is actually in this union. So if X is in U, then by definition this X is in this basic set Bx, and this basic set is contained in union of all basic sets. So we chose X to be an element of U, and we proved this X is an element here. That means this U is contained in this union. Hence U is contained in the union of these basic elements. Therefore U is actually the union of these basic elements. Hence we proved that any open set in this topology, I mean any set of any open set of X, is actually the union of these basic elements. So this proves. So hence every open set in X is the union of some basis elements in B. So one should remember this lemma. So what we proved here, what this result claimed. So this result claims that if you have a space X and you have a basis for X, then this basis generates a topology tau on X. Then this result says that this T is actually the set of the collection of all unions of elements in B. That means if I take any open set u of X, if u is in the tau, then this u is union of some basic open sets of this tau. And if I look at the union of any basic elements, I mean if I look at the union of basic elements B, then that union has to be an element of tau. So let us prove the other result. So we have this lemma here. So this is another lemma. Let X tau be a topological space let D be a collection of subsets of X with the condition that for each open set u of X and for each X in U there is an element, say D in fancy D, such that X is in D and this D is contained in U. Then this D is a basis for X. So what we are given? We are given a topological space X tau xt. So this is our given topological space, and this D is a collection of subsets of X with this condition that if U is any open set in X, i.e. if U is in this T, then for each X in U we are able to find an element D in this fancy D such that this X is contained in D and this D is contained in U. Then we have to prove this D is a basis for X, i.e. we have to prove this D satisfies the two conditions for a basis for a topology. So let us prove this. So the condition first is that we have to prove for each X in X there exists D in D such that this D contains X. So this is the first condition. So we must show that this D is a basis. So this is the first, that is what we have to prove, this D is a basis. Now to prove D is a basis, we have to prove the two conditions for D to be a basis. Now since X is an open set, since now we know that if this is a topological space, then X belongs to this fancy T, i.e. X is open. So since X is an open set in X, then by this hypothesis, because we are given that for any open set U of X, we can find an element D in D which satisfies this condition. So since X is an open set in X, then there exists D in this fancy D such that X is in fancy D, sorry, X is in D and D is contained in X. So this shows that this D satisfies the first condition to be a basis, which is precisely this condition, that if we have any little x in X, we are able to find D in D such that this X is in D. So we have proved this here. This X was given, and this X is in D and this D is contained in X. So this shows that first condition of this shows the first condition for D to be a basis. So actually this is the collection of open subsets. Sorry, I forgot to mention this. So this D consists of the collection of open subsets of X. Then this D is a basis if this condition is satisfied. Now to prove second condition, so to prove second condition, let us suppose now to prove D is a basis, it remains to prove that if we have an element X in the intersection of two elements in this fancy D, we should be able to find an element D3 with the condition that this X is in D3 and this D3 is contained in this intersection. So let us pick an element in the intersection. So let X belongs to D1 intersection D2 for some D1 and D2 in this script D. Now note that this script D here, this is the collection of open subsets, and we know that intersection of two open subsets open. This means that D1 intersection is D2. So since D1 and D2 are open subsets of X, then so is their intersection. D1 intersection D2. So this D1 intersection D2 is open. Now if this is open subset of X, then for open subset of X we are given this condition, that for any X in the open subset U, we have this condition. We can find a basis, we can find an element D in this fancy D with this condition. So then by given hypothesis, we can find D3 in fancy D such that X is in D3 and this D3 is in this open set. So this shows that this fancy D satisfies both conditions of for a basis. So this shows that this fancy D satisfies second condition. Second condition for second condition of being a basis for X. Hence this D is a basis for X. Now it remains to prove, so we were given that so it remains to prove that if X is this topological space and this T be a topology generated by the basis, then this D, which we just proved that this D is also a basis, then this D generates the same topology T on X. Now to prove D is a basis for topology T, we have to prove T is T prime. So since this D is a basis, so let T prime be the topology generated by this D. So what we have to prove, we want to show that this T is actually T prime. So I mean we have to prove every open set in T is also in T prime and vice versa. So let U belongs to this fancy T. Now if this U is in fancy T, then this U is open, and this, if U is open, then this satisfies this hypothesis. Then U is open, and hence by hypothesis there exists some D in D such that X is in D and this D is contained in U. But by the definition of topology T prime, which is generated by T, this U has to be an element of U prime. But T prime is the topology generated by this fancy D. So then an element, say V in this tau prime, I mean V is open with respect to this topology if and only if for each X in V we can find an basic element D in D such that X is in D and this D is contained in V. So this U being an element of tau, by given hypothesis we have this expression, but at the same time this implies that this U has to be an element of T prime, because T prime is topology generated by T, but T prime is a topology generated by T, and hence this U also belongs to T prime. This shows that this shows that t is contained in t prime. Now let us prove the converse, i.e. T prime is contained in t. So now let u prime belongs to t prime. Now t prime is given to be the topology generated by the elements in this fancy D. So hence, so then u prime is the union of elements of D, because we just proved above that if X is a topological space, Xt is a topological space where this T is generated by the basis B, then this T is actually this T equals to the set of all unions of these basic elements. So here u prime is in t prime, then this u prime is actually the union of elements of D. Since each element in D belongs to this T, then so is any set which is union of elements of D. So since each element in this fancy D belongs to T, then so is any set, and so is any set which is the union of elements of D fancy D, because this T is a topology and hence it has to be closed under arbitrary unions. So in particular, u prime is in T because u prime is union of elements of D, and knowing that this T consists the union of any union of elements of D, so in particular u prime is in T, that is T prime is contained in T, hence T and T prime are actually the same topologies. Now when topologies are given by bases, it is useful to have a criterion in terms of bases for determining whether one topology is finer than other. One such criteria is as follows. I mean, if X is any set, so we have this lemma here, so let X be any set, so this is any set given, if B and B prime are bases for the topologies say T and T prime respectively, then the following are equivalent. First item is T prime is finer than T. Second is for each X in X, So actually what we have to prove, what we are looking for, so we are looking for, so we are given a set X and two topologies T and T prime, for which we have the basis B and B prime. Now we have to check which of these topologies find in terms of their basis. So this is the criteria for that. So we say T prime is finer than T. So if this is the case, then this is true. I mean, for each X in X and each basis element B in B containing X, there is a basis element say B prime in B prime such that X is in B prime and B prime is contained in B. So T prime is going to be the bigger topology than T if the basis element of T prime are smaller than T. So this is in some sense the reverse argument. I mean, this topology T prime is going to be largest than T if the basis element of this largest topology are smaller than the basis element of this weaker topology, I mean the coarser topology. So proof. So first we are going to assume, we are going to prove first implies second. I mean, we are going to assume first is true. So let T prime is finer than T. So this is our assumption. So we have to prove second. That means we have to prove if we are given an element X in X and a basic element B in B which contain X, we have to prove there is some B prime in B prime with this condition. So let this is true. So suppose T prime is finer than T and B be an element in fancy B with which contain X, which contain this, I mean B is a basic element in B which contain this X. So what we have to prove, we have to prove there is some basic element B prime in fancy B prime such that X is contained in B prime and B prime is contained in B. Now this B is a basic element for topology tau, so hence this B is an element of tau. So since B belongs to T and B being an element of this basis B for topology tau, I mean this is straightforward, I mean here. So we suppose this T prime contains T and we choose a B basic element B in B with this condition. Now since B prime is the basis of topology T, that means every basic element in this fancy B is here. So if this B is a basic element in T, so this B is content belongs to this T, but T is contained in T prime. That means so then B is in this T prime for all B in B. Also, so this is true. Now T prime being generated by B prime, then for any open subset B of J prime, there exists b prime in j prime such that we had a condition that x is in b prime and b prime is contained in b. So since this b is in t prime, that means b is an open set, and by definition of this basis b prime of b, we have the following. So now t prime being generated by b prime then for the open set, since this b is in j prime, therefore this b is an open set with respect to t prime. Then for the open set b in t prime, there exists this basic element b prime in b prime such that x is in b prime and this b prime is contained in b. So this proves the second item. So what we did, we chose a basic element b here and an element x in this b, and we find an element b prime in b prime with this condition. So this proves second item. Now let us prove the second item. I mean, second implies first. So we are given that, so suppose for each x in x and each b in b with x in b, there is a basis element b prime in b prime such that x belongs to b prime and b prime is contained in b. So we are assuming the second item, and we have to prove the first item. I mean, we have to prove the topology t prime is finer than t. Now to show that, we are going to pick any open set here and we prove that set is open with respect to this topology as well. So let u belongs to t, I mean u is open with respect to topology t. So we wish to show that u is in t prime as well. So this is what we want to prove. Now since b generates the topology t, there is so since this is this b generates this t, then for an element x in u, there exists b in b such that x is in b and b is contained in u. Then by definition, then by hypothesis, so this is our hypothesis. If this is the case, if x is in b, we can find a b prime in b prime with this condition. So then by hypothesis, there exists b prime in b prime such that x is in b B is contained in B prime, sorry, X is in B prime and B prime is contained in B, but B is contained in U, that is X is in B prime and B prime is contained in U. So we have shown for this open set U, and for any element X in this open set we are able to find a basic element B prime in this fancy B prime with this condition. So this means this U is open with respect to topology T prime as well, i.e. this means this U is in T prime. So hence U is in T prime, therefore this topology T prime is finer than T. Now one should remember that if this topology is finer than T, so what this lemma was stating, that a topology T prime is in with our topology T prime is finer than T means that in terms of basis, the topology and the basis for this topology T prime and the basis for topology T, I mean if this B prime is basis of this topology T and B is topology of T. Now if this T prime is larger than T, implies the basic elements of B prime are smaller than the basic elements of B.